All right, so today is sort of, I guess, a paper implementation, but also a broader sort of basis for things. So we have sorry, I should say the discussion for today is on data re-uploading. So this is kind of a somewhat common, I guess. I don't know if there's been enough papers to call anything common. But data re-uploading it comes from a paper called Data Re-uploading for Universal Quantum Classifier. And so in this, they proved that a single qubit using this data re-uploading technique can be a universal classifier. And so I'm not going to really go through the proof because, to be honest, it doesn't really matter to me. I mean, it's useful to know that a single qubit using this technique can be a universal classifier, but it's not particularly relevant as to the exact proof. I mean, it's the same thing with neural networks. I know a single layer or a single hidden layer neural network is a universal function approximator, but I don't know how they prove that, but it also doesn't really matter when you use neural networks. So on this, I'll be sure to link the paper. Basically, the idea is that you have this, the concept, right, of data re-uploading is normally when you have your, sorry, my mouse is just kind of acting up. Normally when you have your quantum variational circuit, you have your QVC, right? You have your, oh my God, my mouse. You have your initialization, and then the standard format, right? You can see is sort of these three ideas, right? You have your encoder. I'm drawing really badly because my mouse DPI is not lowering, so it's very hard to draw. You have your parametrized layers, and you have your readout ops. So this might be your measurements. And so this is the general format, right? So you got your data, and in this case we're talking about classical, although I guess you could do this with quantum data. There's nothing actually preventing you from doing this with quantum data. It might require a slight modification in how it's done, but we're just considering classical data for now. And so what this basically says, instead of doing this sort of framework, let's do this. Let's intersperse this in here. So we do, if E is the encoder and U is the parametrized place, rather than just doing E and then U, layers of U, right? We can instead do, oh, this is so annoying to draw with actually. We can do these alternating layers. So we have E, 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 U, 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 E, 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 U, and so on. And so basically this idea of saying we're encoding at the beginning is not true. You encode at every single layer basically. So the idea of layers is the same, but rather than having these just parameterized gates at every layer, you also encode at every layer. And so the idea here is you have one, you have your encoding layer, you have your parametrized layer, and we're just considering a single qubit case here, yada yada yada. So basically what this what this looks like, right, is you have the final circuit, which is this parametrized thing, and you have these layers of theta equals, and you have this I should really do subscripts, right? These are n, L of, right? These are, so you have this arbitrary depth circuit, right? It doesn't matter. And so the idea is that by re-uploading the data, that's what's this intersparsing of the encoding is. That's what the re-uploading is. By interjecting this classical data or quantum data, but in this case we're just working with classical data, every layer or every operation, you can create this nonlinearity necessary for the universal quantum classifier, universal classifier. So you can look into the paper to see their proof. It's pretty short. I don't think it's particularly complicated, but this is the sort of framework that they present. But the one I use here and the one they first presented are slightly different because I used their second formalization. Specifically, you can combine these into a single parameter, right? So, or a single operation, I shouldn't say parameter. And so previously, right, this basically just doubles the depth of your circuit because you have to do this encoding all the time. So you get these super deep circuits. But what you can do is, right, you have your unitary operation, which, you know, has some parameters. And you have your encoding operation, which this also has parameters, right? This isn't mentioned here, but when you're encoding the classical data, this you can get some of this nonlinearity because, right, you have your, let's consider the theta here, right? You have your typical quantum variational circuit parameters, but also when this data, right, comes in, you also have this classical parameters, and it's just the same concept as you know, neural networks. You take your weights and you multiply it by the inputs, and that's all you do. But this weight here is not normally added, or might not normally be added, depending on what kind of encoding scheme. You might have some sort of quasi-learned encoding scheme, in which case you would be familiar with this, and there have been papers that have done things as that. So that might not be completely new to you or to your experience, but in this case, it's somewhat different than the standard framework of encoding. And so we can combine this into one sort of operation, right? So for a given operation, right, we're combining the U and the E into just one layer, basically. So this is a single layer. We do this unitary operation where we have the parameters of that layer, and we add them. Oh, that's my bad. To the input, right? So this combines the depth, right? And so this is the same functional sort of approach, right? You're re-uploading things, but you're sort of re-uploading it directly into the parameters, which is kind of confusing but more efficient, right? Because then you don't have to do, like here in this original approach, you have, for every depth you'd have to have 2 operations, but now you only have to have 1 operation. And so this is where this comes in. And so there's you can see, right, for this unitary operation, this scales with how we can choose this to be different things. They choose it to be like just a unitary gate, right, which has the 3 parameters, and you can directly code that in some like languages, like Penny Lane has I think it's ROT command or something, where you can directly access those 3 parameters. I just use a breakdown or a decomposition of this unitary into RY or Z or Y. But you can see that each one of these operations has 3 parameters. Oh, I cannot write pair. I'm just going to do that. And so This makes sense, right? If your data is less than 3, then you can easily access this. There's ways to consider that if you have more than 3 parameters and or more than 3 input, right, and you want to do different things, there's a whole number of ways that you could construct this for a variety of inputs. For example, you could do multiple, right? So if each one of these are built on 3, then you could, for each layer, basically do this operation, however many times you need to. For if the input is 20 times long, then you could repeat this 7 times, and then that would constitute a layer. That'd be a really big layer, but it would be doable. And you can also imagine multi-qubit examples. This is all thinking of a single qubit for re-uploading, but you can do multi-qubit examples where you have 2 qubits, you can entangle them maybe, and then you have at every layer, right, you have these operations on each of them. And so you can encode the data into these either symmetrically in that these both have the same data, or asymmetrically in that some data goes in this one and different data goes in here. And this is what I'll show. And so you can sort of envision this any way that you want. It's really more about the practical use. I mean, it's neat that there's a universal approximator or classifying theorem. That's a neat thing, but in terms of using this, you really just want to experiment and see what can work. And so here we can get into the code a little bit, and we can see that how this is implemented. And what it's going to be using is a custom layer in Tensorflow-Quantum, which is a great thing to know how to do, is to make these custom layers. And so we'll go through that. And just one more note, in the original paper, they present a fidelity-based cost function, but I don't use that. I don't really know why they chose that cost function. It's like you can just use other things, but okay. Especially since fidelity can be an expensive operation to compute if you use more than 1 qubit or lots of qubits. And so, yeah, now we can consider, let me go over to that. There we go. So now we can consider this data re-uploading layer, right? And so what is this going to do? This is going to be our entire model, basically. It's not just going to be a layer, although that's how it's classified. So the goal, right, is to take the input, encode it, do the operations, and re-upload. And so that's hard to do, right? Because let's think about how TensorFlow is designed, right? Normally, let's see if I can do that. We have data that goes to encoding, that goes to params, that goes to out. And so if we want params to not params to etc., right? That's not really doable in basic, just using the default layers. So what we do here is we use some custom layers, and we'll go through it. So first, if you've never, well, 1, standard imports, and 2, if you've never created a custom layer at all, you should learn how to do that. It's a great, not just in TensorFlow-Quantum, but in normal TensorFlow. It's really useful to build these custom layers because it can make it easy to work with, format things, and get gradients all through this. So we define it, and it inherits from the TensorFlow layer class. So it takes however many qubits we have, the number of layers, and the readout ops. That's what defines this layer. And so, right, the number of parameters is however many qubits we have times 3, right? Because there's 3 params per operation, times the number of layers. So then we just define these layers. That's the number of layers. This is the list of qubits. So now we define 2 weight vectors, theta and w. They're both initialized randomly, and they're both trainable. And so basically what these correspond to, right? Theta is your standard weight vector, or standard, I shouldn't say weights, but standard parameter vector for any variational quantum algorithm. And the w, right, that's the weights for the input, and that determines what you multiply the inputs by. And then we create these params, or we create these circuit parameters, right? That's what these are because we already have the values. And it's worth noting that each of these has the length of number of parameters, because when we're feeding it into the circ or the circuit, right, it doesn't know that we're adding parameters together to get the final parameters. It just knows that we did these. It just knows that this is a parametrized gate. It doesn't know that two parameters are added into it. And so that's something just that you have to be aware of, right? Oh, that's weird. It should be a 0. And so, yeah, when you're looking at this, you can see a lot of the ideas here that you've seen in the variational quantum eigensolver videos, where we use some simple custom layers there. And so now we do the controlled PQC, and this is going to be the most complex part when we put things into this controlled PQC, because it's going to be right? We have some static parameters, right, which is the input, right? I mean, the input is given, so we don't control that, right? Those are sort of non-parametrized things that we're given. And then we do have parameters, and so that's going to be a little complicated, but we'll get through it. So we have our circuit, we have our observations, and we have our standard adjoint differentiator, which I just used for speed. We have our default input circuit, which is just an empty circuit. And then we can create our the design of our circuit, right? And so this is all done in the initialization of the layer. And so basically all we have to do is create X layers of this. And so the way we do this is we just do RY, RZ, RY with each of the params on the given qubits, however many there are. And then we do C0 to entangle them if there are multi-qubits, if it's not just a single qubit classifier. And so once we create this circuit, right, we have this layer. So now we need to say, okay, when we're given these params, or we're given these inputs, sorry, what do we do with our parameters, our params, to get the output, right? And so this is probably the first time I've ever written comments in this code, right? And that's because a lot of TensorFlow operations are not very intuitive, and I often find myself having to go to this documentation and stuff like that. And so basically, so the input, right? If we're doing some sort of batch training or not batch training, the batch size could be 1, but there's some length to this input, right? And this should be in size. And so this could be, right, if we're doing circuit training with batch input, this could be 32, and then whatever the input size is. So this could be the classical data, could be size 100, right? We could have a length 100 array, or could be size 10 or whatever. And it should be noted that this isn't perfect code, because there's no errors or there's no flags, right? In size is sort of implicitly defined already, because we say, okay, if we're giving these parameters and we're defining all this, and then we're assuming that the input size is something. And so by defining the number of qubits, since we're saying there's 3 possible numbers or encoded bits of information in each qubit, then we're sort of limiting it, right? That the inputs have to be less than or equal to 3 times the number of qubits. And that's not something expressly mentioned or there's flags for. It's just that should be noted, that's built in to assume that you're doing it correctly, and it won't like tell you you're doing it wrong. So we get this batch size, right? So we get the shape of the inputs, and then so that'll be, for example, it might be 32 by, well, let's assume it's like an ImageNet thing. It'll be 30. And we're doing size 100 batches. So it'll be 100, 32, 32, 3, right? Because they're 32 by 32 images, and there's 3 channels for the color RGB. But the batch size, right, is the first or the 0th index. So we get this first element, or we get the batch size, which is the first index of this shape, because we're given, however many examples of this. So now we take this circuit, right, which is a 1 by 1 array currently, and we create a batch of them, however big. we need to, right? So we can repeat this. And the reason this is done is so that it's batch size agnostic, right? We could say, oh, we could easily hard code this for single inputs or 32 batch size, but we want it to be agnostic. And so this is what's showing. It's showing the size transformation of the operations. So we repeat this batch times, right? This input circuit, this empty circuit. So then to generate the inputs, this is maybe not the best terminology, right? But the inputs to the whole process or to this call function is different from the input circuits. This is the classical numbers, right? This is the data we're encoding. And so what do we do here? Well, we have to reshape it, right? Because currently it's batch times size, right? It's just a default input size, but we want to reformat it so that it's in the same shape as the number of parameters. And so we keep the batch the same, but it could be, for example, the number of parameters here could be 26 or something. No, that's weird. Let's consider 3, right? But if the input size is, or this could be 6, could be 6. Oh, did I mess it up? Self.num. There we go. Then we're just sort of lining this up. And so this is where there's sort of an extra check to ensure that the input size matches the aligns with this number of parameters. And so because keep in mind the number of parameters is for all layers. And so what this is really saying is just, okay, we have, let's suppose it's 3, right? Let's suppose we're doing a single qubit classifier. The input is size 3, but we have maybe 10 layers. So if we have 10 layers, then we need to, if we're going to multiply the weights by this input, and this input is static, then we need to basically expand this input to match the dimensions of the weight vector. And so this is what is happening right here. We're expanding it, we're tiling it, which is an operation to basically repeat it a certain number of times. And you can see this is not very intuitive, right? Like, what is going on here? But this basically, don't change the first dimension of it, we're changing the second dimension, and we're tiling however many we need to on top of each other, or extending it that many times. That way we can multiply them together. So now we get this weight vector, which is 1, 1 index of the number of parameters, and we multiply it by batch times number of parameters. So we get this new vector, which is the weights times the inputs. Now we can add them with the thetas, but before we do that, we need to reshape the thetas, right? Because currently they're 1 common number of parameters. That's the shape, right? There's just one array, and we need to reshape that so it's the batch size. And so now that we have the final thing that they're both batch common num params, or they're both, they both obviously contain the number of parameters. That's how long they are. But now that they're both of the batch size, we can create the final parameters array, right? This is the final thing that we want. And so now this is this controlled PQC layer that we're feeding into, right? We're saying we're going to define all the weights. You don't, Keras or the behind the scenes doesn't handle any of it. We're managing the weights down here. And so now we feed in the input circuits, which has been repeated for the number of batches, and the defined parameters that we went all this work to define, and then we return that value, or those values, because it's size batch. And so this is kind of complicated, but it doesn't, we don't have to worry too much about it, because once we call this, all these operations and stuff will be handled by the magic of TensorFlow's auto differentiation. We don't have to care, because they're all valid. Like, these are all valid TensorFlow operations. We can just say, hey, look, you deal with it, TensorFlow. I don't know how this stuff changes the gradient, so you handle it, which is really a nice thing you can do in TensorFlow custom layers. And so now that we have this data reuploaded layer, which is kind of it takes a little bit of work to do in Tensorflow-Quantum, but once you have this custom layer knowledge, it's pretty straightforward. Now that you have this, we can do some analysis. So basically, I'm just going to do some comparisons. I'm not really going to walk through the code that much here because it's all code from the excuse me, from the variational quantum classifier video, but I will show the results. So we can see first that we have the, which one is this? Okay, I'm just making sure I keep track of what's what. So here is, yeah. So we have, okay. 1 second. Okay, so we can see, yeah, these are some examples of the applications on some of the data from the variational quantum classifier video. And so here we can see this is a circle one. And so remember that the data here is hold on 1 second. You can see here that the data is just 2 inputs, right? An X and a Y coordinate basically for where this circle data point is at. And I won't go through this quantum NN. This is exactly code copied from that video. So you don't have to wonder where it came from. The explanation is there. And so we fit it using 100 epochs, early stopping of 10 and batch size of 32. And now we can create the reuploaded one. So this time we use a single qubit for the classifier. We read out in the Z direction instead of using some sort of fidelity operation. This time, unlike what is common in TensorFlow-Quantum, which is having the string input type, we have an input type of 3 numbers, right? And so it's important, this is different, right? Because when we call it, right, in that call function of the reuploaded classifier, we expect numbers because it's handled differently. So this is why we don't use data type string. So we create it using the qubit, the layers, and the readout operators. And then we can create the model, use the same exact optimization sort of routine. We just use mean squared error here. I don't know why. I actually wrote this code a little while ago, so maybe it just works better. But the one thing we do have to do beforehand is pad the data, because remember the data is 2. There's 2 inputs, but we expect it to be 3. And so we just pad it, 0 pad it basically. And then we can fit it. And so we can see, let me just bring it up if I can. Go to ReUpload, go to circle, compare. And now let me add this as a screen share. Yeah, so you can see here, there's early stopping. That's why it stops earlier. And this is obviously validation accuracy, but it's worth noting that you can see the the power of just 1 qubit here. We'll see momentarily too, when I go through the code, the power of a single qubit for even more inputs. So let's go to that part next. So I'm just gonna X out of that. Let me delete that window capture. So now we can see this is the blob. And so remember, these are little blobs next to each other. And so this time there's 6 centers. So once again, this is the same data type. There's an X and a Y value, but this time there's instead of it being binary classification, it's, hexa classification. And so what we can see here is the same exact code from this blob video, or this blob section of the variational quantum classifier video. But down here, we instead have 10 layers of a single qubit. Remember, this is a single qubit quantum classifier with data reuploading. Once again, reading out in the z direction, we have the 3 inputs, right? Because we're padding the inputs. We create the same way with the qubit, the layers, and the readout operator. But this time we need a modified loss function and a modified accuracy, right? Because we're getting a number between -1 and 1 when we do the expectation value of the z of the z operator. So if we want to convert -1 to classes between 0 and 6, basically, then we need to modify this. And so we can say this is basically accuracy, right? Accuracy is just this, like this line means accuracy, but we have to convert the y prediction into that format, so we can add 1 to it, right? So now 0 to 2 is the range, and we multiply it by 3, and we'll get 0 to 6 as a range, which is what we want. And this is, once again, we do the same thing for the loss, right? It's mean squared error, but between these modified values. And we can see once again that this is a example of the power of the custom differentiation, right? This auto diff, you just do these operations, right? The auto diff will handle it. Like, I don't want to deal with figuring out the gradients of this. I mean, obviously you take a derivative of this. It's just, this 1 falls away and it just becomes 3, right? The derivative of 3x is 3. And so it's not complicated, but it's something that's all handled by TensorFlow, and this is sort of like the custom layers, right? Instead it's just custom loss. And so now we can train this whole thing using this modified loss and modified accuracy. Once again, the same training parameters, 32 batch size, epochs 100, and we can compare the accuracy. But one thing it is worth noting is that we see a much more advantageous situation here, because with the circle there was just 2 qubits, right? And that's how we encoded the data. But here there's 6 qubits, right? Because there's 6 blobs, and so that's how I decided to encode it. And so it's important to note that we're seeing 6 qubits to 1 qubit. That's a big advantage. And depending on the type of hardware, the situation, right? At least in simulators, it's a lot easier to simulate depth than it is to simulate width or number of qubits, because qubit simulation, or at least state vector simulation, increases exponentially with the number of qubits, but only effectively linearly with the depth of the circuit. And so having a really deep circuit but a really small number of qubits is ideal for simulating. Well, I mean, obviously small depth, small qubits is ideal, but it's better than having, or it's faster, I should say, than having lots of qubits. Whether or not that's the case on hardware probably depends on your type of hardware. But we can see that in this example that I don't have all of the information right here because I'm actually running it in the background. There were some errors in this code earlier, but we can see that if I bring it up, let me add a new window capture. So yeah, we can see here that reuploading does pretty well with just a single qubit. So now the last thing we're going to do, you can see this graph of accuracy. Last thing we're going to do is compare on the regression task, which, if you remember, used a lot of qubits, specifically 13, because there's 13 inputs. And so what we can see here is this time we use 5 qubits for the reuploaded parametrized quantum circuit, because there's 13 inputs, and 3 times 4 is 12, 3 times 5 is 15. So we need at least 15 input size to capture all the information. And now you could do this with less qubits and just assign more depth basically to each layer. So each layer is multiple unitary operations of 3 weights and inputs instead of going the number of qubits way. I just wanted to increase the number of qubits. because I wanted to show the entanglement operation and prove that it does work for multiple qubits. But you could do this with a single qubit, and that's probably a worthwhile experiment, right? Modify this code right here, and it might require some modification of this code. I'm not 100% sure, because if you want the depth, no, I don't think you could work with this code and just say the number, like basically mislead the number of layers by multiplying this by however many more you actually need. But that is something you should try out and see if it works, and that would be really cool actually if it does work. But you can see here that this time we have an input shape of 15 because we're padding it, right? It's 13 to 15, and we train it pretty much the same way. There's mean squared error here. It probably shouldn't be mean squared error exactly. I should probably do some modification because I don't think you have negative housing prices, and so it doesn't really make sense that half the outputs are meaningless, but that's okay, because it works for the most part. We can see the output. This time we have to plot the loss, right? Because there's no accuracy. So we can see it doesn't quite learn as well. You can't see that yet. As well as the 13 qubit version. You can see, but the loss is still decreasing after 200, and this is validation loss, not training. And so it's still decreasing after 200 iterations, so you could leave it running longer. It's worth trying the modified loss function too, because the negative numbers are useless. So what you could do is basically add 1 to it and divide by 2, and that would, or just add, yeah, and that would achieve the same goal, because you're scaling it then from 0 to 2 and then 0 to 1 by dividing by 2. Or you could try the single qubit classifier or something like that. All of those would be worthwhile endeavors, I think. And so we can see now how to do this data re-uploading in Tensorflow-Quantum using these custom layers. And so, yeah, all of that will, of course, be the code, and paper, of course, will be linked below. And that's it.